So we're going to start with using calculus, multivariable calculus, to figure out optimal acceleration for running when you're going up a hill, given certain constraints. So let's begin. First, we need to start with our old integral definition of work, which is that our work is equal to the integral from point A to point B of a force and the dot product with the displacement that's going on. So in this case, for our purposes, we're going to assume an inclined plane for figuring out this, and we're going to give it an angle theta. And at this angle theta, we are going to be a person. Let's simplify the person so we can see the forces better. What we have is we have a force of gravity that's going on here, which we can't really use. So we're going to split it into a force that's parallel to our surface and a force that is perpendicular to our surface. Now, what we care about is we care about the amount of force applied here. And in order to keep a runner going in constant motion, we need to make sure that all the forces are in equilibrium. We don't really worry about this normal force right here because that's just equal to the perpendicular force into the plane. And then we have the force that we are applying here to be equal to the parallel force. Well, in this case, our parallel force is going to be the force of friction that's driving us back. So to do this, we require this thing called the friction coefficient mu, and that's just a ratio between two surfaces. In this case, it's going to be the rubber over shoes and the dry asphalt or wet asphalt, which have two different mu's, and that relates your coefficient of friction to this normal force, which is, in this case, because it's in equilibrium with the perpendicular force, we can just use perpendicular force to figure that out. And if we draw a triangle here, we can see that with angle theta, that this perpendicular force, Fn, is going to be equal to our gravitational force multiplied by the cosine component, because it's the adjacent component, so it's going to be mg cosine theta. So now what we care about is Ff, which is equal to Fa, our force applied, and that's the one that's going to be used in our work function because our displacement is going up the plane, and so is our force. So our Fa, if we solve for our applied force, Fa will be equal to mu mg cosine of theta. So we can substitute that in, and eventually that means that the work that we do to make sure that we don't go back, that we go at a constant velocity upwards, is going to be work is equal to the integral force with dot distance, so we'll just multiply those. So if we substitute this in for the force, mu mg cosine theta times our displacement, we'll call it x for now, but we won't be using it for a while, so it doesn't really matter too much. All right, so now we have this. Let's go back to other things, that when you're going up a hill, you're also increasing your potential energy. And how do we represent our potential energy? We can represent that with our change in potential energy is going to be the mass times the gravity times the change in height. And what we want to do is we want to add this on, so we can just move this here, mg delta h. But what we don't care about is our work, we care about our power, because we want to have a constant power. And the way we relate work to power is that we know that power is equal to the derivative of work with respect to time. The first derivative of work with respect to time, so we're going to do that on both parts of this. Let's start with the first one, dw dt is equal to power is equal to, mu mg are always going to be constants, at least we're going to assume that g is a constant, it's pretty much a constant, and because we're taking this with a derivative with respect to time, so we're going to have to go ahead, let's take all these. So this one's the easier one. Let's start off with h, it turns into dh dt, and then with mu mg, because theta right now is currently a constant as well, so all we care about is dx dt. And what we know from earlier as well is that our velocity is equal to the first derivative of displacement with respect to time, and our acceleration is equal to the second derivative of displacement with respect to time. So, and this will be very important later, but for here, we can substitute them out. So we can bring this down, and we know that our power is equal to mu mg cosine of theta times dx dt, which we found here is equal to our velocity, so v. And then dh dt is our change in height with respect to time. Well, we can think about that as our change in height with respect to time and this is our change in displacement with respect to time, which is equal to v. So in other words, we can say that dh dt is just a sine component of v. In other words, dh dt is just equal to v sine theta. So we can substitute this in as well. We can bring that down to plus mg v sine theta. So now we've defined everything in terms of power, but we don't really care about that. We care about power when all constraints besides angles are held constant, or in other words, that just means we have to take a partial derivative. So let's erase all this and bring this back. So again, acceleration is the derivative of velocity with respect to time. We established that earlier. So from this, we're going to take the partial derivative of power with respect to angle theta. And this is going to be relatively straightforward because we're going to isolate, or we're going to bring all the constants over, or non-integrated. So mu mgv cosine theta. So this cosine theta, the partial derivative of this entire thing with respect to theta, we're going to take cosine theta. We're just going to take the derivative of this with respect to theta, and derivative of cosine is negative sine. So this is going to be negative sine theta. And then the other side, we also have to have mgv be on the side. And then sine theta, the derivative of that is just straightforward, it's just cosine theta. So this is what we get. Let's just make this look a bit nicer. We'll bring this down, so that would be mgv, and we'll factor out mgv, or it's already factored out for us. We'll move the mu back in, so then we get cosine of theta minus mu sine theta. All right, let's get rid of this. We need more space. So now what we want to see is how this changes with respect to time, because we want to keep that constant. We want to keep our power constant. So we're going to take the derivative of partial derivative. Derivative of time of the partial derivative with respect to angle, and that is going to give us, well, mgv we can still hold constant for now, and we're going to take, no, v can't, now this time we can't hold v constant because v is going to be, v is also dx dt, it's with respect to time. So here we have a product rule. It's going to be a little bit ugly, but we can still work our way through it. So the product rule states that it's going to be first times the derivative of the second. So the derivative of the second, cosine of theta with respect to t, so that's going to require a chain rule. Cosine theta, normal derivative, would be negative sine. So negative sine theta times d theta dt. Negative sine theta d theta dt. Subtract mu sine theta. Mu is just a constant, and sine theta, we're going to take the derivative of that. It's cosine theta, but chain rule, so minus mu cosine theta d theta dt. And we'll close that partially. So this is our first part of our product rule. The second part of our product rule requires that we take the derivative of the first one, well, dv dt, but for sake of brevity, we'll just change this to what we defined earlier as acceleration, and the next part gets to remain the same. So we'll keep that cosine theta minus mu sine theta. So after we execute our power rule, we'll consolidate everything together. And what we want for this is we want this change to be equal to 0 because we want to have a constant power regardless. So this is going to equal 0. So we can take this thing and we can bring them to separate sides. So we'll start with what we have, this nice thing over here. We can, first of all, we can eliminate mg because all is equal to 0. And mg, it doesn't matter what it is, it's just a constant. It doesn't affect anything. So let's get rid of what we have up here because that's just blocking our way. So let's bring out mg, and we can move this entire v term, this entire part of the product rule, we can move that to the other side. So now we're left with a, so the right side, a cosine theta minus mu sine theta equals v. And then because these got moved to the other side, so we'll turn them positive, sine theta d theta dt plus mu cosine theta d theta dt. So here we want to isolate acceleration a, but before we do that, we have something that we can do to make our lives a lot easier, is we can consolidate things to turn into tangents, because tangent of theta is just a slope. So if we know the slope, it just makes it easier for us to calculate in general. So let's divide everything on both sides by cosine of theta. So a cosine theta, that's just a minus mu sine theta, a 1 minus, and we also have to divide this one, mu sine theta cosine theta, that's tangent of theta. So tangent of theta. And then this side, we have v, so, and then sine theta d theta dt, we do the same thing, tangent theta now, because you divide that one by cosine theta. And then this one, cosine theta divided by cosine theta, that's 1, so we eliminate that, mu d theta dt. Running out of space here, so let's get rid of this bottom one. So what does this mean? Well, what we want to do is to help us figure out how to run, we care about what our acceleration is. How do we change it as we run up a hill and how the hill changes. So acceleration is going to be equal to v tangent theta. We can actually factor out those thetas to the side. So that's just going to be v d theta dt, tangent of theta, plus mu. And then for the other one, and then we bring this over the bottom, divide it, so it's 1 minus mu tan theta. So now we have this equation. This lets us know that our current velocity, the rate at which the angle of the hill is changing, the current angle of the hill, and our friction coefficient, which is already predetermined, we can use that to actually figure out what we should do given certain situations and optimize our running ability. So how does this work? We're going to plug in some values just to get a gauge for how it works. But let's start with easiest one, which is we only need one value that we care about, is d theta dt. Theta is our angle. So if our angle is not changing at a given point, and it looks like this, then this would be our inflection point when d theta dt is equal to 0, right here. If d theta dt equals 0, our acceleration is 0. And that makes sense. We shouldn't really be changing here. We should be speeding up here and slowing down as we go up. And for other situations, which is a little harder, we want to find an actual numerical value for acceleration. Here, acceleration 0, because d theta dt 0, that's all we need. So we have two constants that I should clarify. Our static mu for dry asphalt and wet asphalt are actually different. So we're going to need to use different values. Mu s for dry asphalt is 0.9. It's very sticky. But for wet asphalt, it makes it a lot harder, and the accepted value is 0.5. So we're going to use these to plug it in. So let's start with a pretty high grade, just for the sake of simplicity. We'll say that our angle theta is equal to 45 degree. It's a 45-degree grade. And our change in angle, this has to be in radians. So in fact, let me turn this to radians because that'll just make it a lot easier. Pi over 4. We'll say that per second, so d theta dt, it's changing d theta dt, it's changing by negative pi over 16 per second radians. So let's plug this in. And also, we'll say that our initial velocity is a good running pace. It's about relatively slow, let's say 5 meters per second. So now we have this information which we could calculate just by measuring the hill and how we're running and what we're running on. Let's plug this all in. So our acceleration now that we would want to have would be 5 meters per second times d theta dt, which is negative pi over 16, times tangent theta plus mu. So tangent of theta, tangent of 45, why I chose it, because tangent of theta has a slope of 1, or tangent of theta gives you 1, that's a slope. So 1 plus mu, which is 0.9 for dry asphalt. And then we're going to divide this by 1 minus 0.9 times tangent of theta, which is 1. This makes our lives a lot easier. So this would be then equal to, looks like we'll get rid of the constraints here. Or not constraints, our variables. So this is just 0.9 times 1, 0.1 minus 0.9, 0.1, so we multiply the top by 10. So that would give us 10 times 5 times negative pi over 16 times 1.9, and I don't have a calculator with me, but we can approximate this. So 1.9, so it's 19 times 5 times negative pi over 16. So that would be about 100 over 16 negative pi, so that's just about 6. Negative 6 pi should be our acceleration, which is a decent amount, but it's only for a short time. So, and it's also it's a very steep grade. So this is what we're going to have to worry about. Let's continue with our next example. So Our next example is, oops, I erased that, that's fine. Hopefully remember that. So our next thing is going to be, we're going to be running on dry asphalt, on wet asphalt, and it's going to be the same thing. A is equal to V d theta dt. We'll say all that is the same, just because it's too hard to come with another one. And then this one, we have, I forgot. I have to derive that again. Yeah, I guess I'll have to derive that again. So I guess this is it for the examples, and thank you for watching and bearing with me for like the last 10 minutes.